So we're now going to build up to the outer product. And we have, in fact, already seen the outer product. This ket on the left times a bra on the right is an outer product. So much like before, we had an inner product that was a bra on the left and a ket on the right. A ket on the left and a bra on the right is an outer product. So we have shown that an outer product of two vectors can represent an operator. So let's take a further look at that, and we'll consider some ket u that represents a linear combination of three functions, u1, u2, and u3, and a bra that is the linear combination of v1, v2, v3. The outer product, then, can be written, of course, ket u times bra v, which in vector format or matrix format is the column vector times the row vector, so column vector u times row vector of v. So if we want to multiply these out, we can follow the rules of matrix multiplication and just go ahead and multiply these out, exactly like we did with an inner product. So for matrix multiplication, what we do is our first row, or sorry, our first element here times v1, v2, v3. Those represent three elements in our matrix. Our second row here times our first column, second column, third column. Our third row here times our first column, so third row, first column, third row, second column, third row, third column. So when we multiply a column vector of length n and a row vector that in this case has the same length of n, we get an n by n matrix. And in general, using a general definition of an outer product from linear algebra, where we have a column vector of length, more generally n, times a row vector of length m, this gives us an n by m matrix. So if an outer product is a matrix and it can, or is an operator and it can be expressed as a matrix, then an operator can be expressed as a matrix. So let's consider then a generic operator. If we have an operator, let's just say W, just a totally made up indicator for some operator, we don't know what it does. And let's go ahead and multiply it by the identity operator twice. We then have our operator W. Our identity operator, recall, is the outer product of A with itself, or the sum over all elements in A with outer product of A with itself. And we'll do that for A double prime on the left and A prime on the right. So we haven't done anything here. We've just multiplied it by 1 on the left and 1 on the right. So W equals 1 times W times 1. But what this does allow us to do is, well, since A double prime and A prime are both kets in some basis, in other words, set of functions, that is n long, this gives us n squared numbers because we're summing over the number of elements in this vector and the number of elements in this vector. So will give us n squared total numbers returned in the form of a double prime w operator a prime ket. And we can arrange those in a matrix where these show up in our rows. These represent our rows and these represent our columns. So we can arrange this as an n by n matrix. Following again rules from linear algebra that I can sort of just skip and show you the answer here. Our W operator then has each of these elements spread throughout. So this is A1 row, A1 column, A2 row, oops, and then this is still our first column, so correcting that there. So this represents we've got all A1s in this column on the right-hand side, all A2s on the column on this right-hand side, all A3s on the right-hand side in this column, all the way up to all A sub n's in our ket on the right. And on the left-hand side, we've got all A1s in our rows, all A2s in our rows, and all A3s in our rows. And so each element in this matrix represents an inner product, which is just a number. So we can express then this operator as a matrix. And this seems like a little bit of complication here, but this will actually simplify things quite a bit when we start to think about operators operating on larger sets of not just A is a single function, but A is a linear combination of functions or a vector that might be many elements long. And so it will still take some work to calculate this particular inner product, say each inner product all throughout this matrix. But what this does is this allows us a really convenient way of visualizing and understanding all of these operations for large ket spaces.